All right, I am going to discuss effective field theory ideas applied to a specific problem in classical gravity. This is, well, originally based on work that I did with Ira Rossi about 10 years ago, and we have been developing it since then. The problem that I have in mind is a bound state of two classical compact objects. By compact, I mean either black holes or neutron stars. Mostly in this discussion, I'll talk about black holes because they're simpler, but the same idea applies for neutron stars. And by bound state, I just mean that they're in a Newtonian orbit, almost Newtonian orbit around each other, separated by some distance. This orbit is not stable because as these things move, they emit gravitational waves with some wavelength, lambda. And then they slowly lose energy and they spiral into each other and eventually collapse. I'm not going to discuss the collapse. The collapse is a difficult nonlinear general relativity problem. Instead, I'm going to talk about the limit where these things are moving pretty slowly. So this is a problem that has a whole bunch of different length scales associated with it. We have the orbital separation between the two objects. Let's call that R. We have the size of the objects themselves. Let's call that RS. We have the wavelength of the radiation that's being emitted. And we also have another scale, namely the gravitational radius. I'm going to call that R sub g. And if these are objects with some mass m, the gravitational radius is the short shell radius of the objects. So for black holes, this gravitational radius can be regarded as being a measure of the size of the things that are orbiting around each other. The non-relativistic limit, by good old Newtonian physics, the velocities are related to this radius into another scale, to the orbital scale, by this formula of diffraction physics. So the typical velocities in the non-relativistic limit are related to a ratio of scales, r gravitational or r orbital. That is assumed to be much smaller than 1. In fact, the velocity is going to be the expansion parameter in this problem. So the goal is to formulate the dynamics of these two objects as an expansion in powers of velocity. And yes, the leading order is a nice Newtonian problem, but well, first of all, the motivation for studying this is gravitational wave experiments and gravitational wave detection. And it turns out that for these experiments, very high sensitivity is needed. So the dynamics has to be understood to a very high sensitivity as an expansion of powers in velocity. So to leading order, it's a nice, simple Newtonian problem, but then the complications due to general relativity start creeping in. And if you want to know this out to some order in the expansion, in fact, the experiments require sensitivity to at least velocity to the 6, so pretty high order in the expansion. And then all the nonlinear features associated with relativistic gravity start coming into play at some order in the expansion. But to really understand where they come in, it's a challenge because many scales appear in this problem. And in the small velocity limit, all these scales are correlated. So we have many correlated scales. And so that makes the dynamics complicated. And in fact, we have a hierarchy of scales ranging all the way from, if we're dealing with black holes, the smallest scale is the gravitational radius. Actually, if we're dealing with anything, the smallest scale is the gravitational radius. So the gravitational radius is the same as the size of the object. It is suppressed relative to the orbital scale by 2 powers of velocity. And that itself is compressed relative to the wavelength, which scales like the orbital scale divided by velocity. That just follows in the multiple expansion. Familiar, for example, from electrodynamics. So we have many scales in this problem, and we could deal with them all at once, but that makes the calculations and physical interpretation of the different effects difficult. So rather, what I want to discuss is how to think about this problem using effective field theory. So the fact that there's all these scales cries out for an effective field theory formulation. So we don't need, but it is quite useful to think about this from one point of view of effective field theory. So once you do things from the point of view of effective field theory, all the usual good things that happen when you write down effective field theories become available. So why treat this using effective field theory? Well, for the usual reasons that you construct any other effective field theory. First of all, there is explicit separation of scales. Manifest power counting and velocity. Manifest separation of what is in the UV and what is in the infrared. So ultraviolet divergences get dealt with in the usual way by counter terms. And infrared divergences in the usual way cancel from physical observables. What else? Well, model independence. If you write down a Lagrangian that has all terms consistent with the symmetries of the problem, you're by definition being model independent. And finally, can use the renormalization group to understand non-analytic corrections. So my goal in this lecture is to set up the effective theory that can handle all these different scales, give you an idea of how to calculate, and explain why it solves, or why I've driven some of these issues. And so we're going to do this, well, like in any other effective field theory, one scale at a time. So if we are viewing this binary in-spiral problem as an effective field theory, well, it's actually a chain of effective field theories. So in a sense, it's a tower of gravitational effective field theories. Starting with the full theory is pretty simple to state. In the case of black holes, which are vacuum solutions, the full theory is just Einstein's equations with no source term. So that is the problem we're trying to solve. Two objects that are solutions of gravity superimposed together and orbiting each other. But instead of solving the full problem at once, we do it in stages. So I guess I should have drawn this tower going down, but I don't have enough space, so I'll have to draw it like that way. So you can imagine going to longer distance scales as an arrow that goes that way. So here's the UV, this thing. And then in the infrared, you go to longer and longer scales. So if you look at scales much larger than the size of each object in this problem, really you can treat the orbiting black holes just as if they were point sources. So this is some sort of point particle effective field theory that contains gravity coupled to some suitable point particle action, which I will describe in a second. If you zoom out even further, so this is at, I guess, length scales L, much larger than the typical size of the orbit of the objects. If you zoom out further, so now L starts becoming comparable to the orbital scale, you approach another theory, which is a two-body bound state. So now the fact that there's two of these objects orbiting each other plays a role, and you have to take into account their mutual dynamics, the exchange of gravitons between them, and gravitons that are being emitted out to infinity. And finally, if you zoom out all the way out, we'll have room on this board now. If I zoom out all the way out, the infrared is not going up the board. I get a theory of radiation only, of radiation modes, coupled to the multiple moments of this system. So, as I said, my goal is to describe more or less how you go from one effective theory to the other. In other words, how to match across the different theories, and then how to do calculations in each theory. The calculations will be done using standard Feynman rules and Feynman diagrams, even though it's a classical problem. I should say, I guess people who are taking this course have been learning about soft collinear effective theory and things of that sort. And this is an effective field theory that whose roots come from the same place. So all this stuff was motivated by similar attempts to describe bound states or similar formalisms for describing bound states in gauge theories, namely non-relativistic QED and QCD. And the effective field theories I'm going to write down have certain features in common with those. But it's actually really more of a hybrid, and the actual effective field theory for this classical problem is sort of a hybrid between NRQCD and heavy quark effective theory. So that's for people who've been following those things. So those are the theories, and let me describe them one at a time, starting from short scales going all the way to long scales. So let me first talk about matching onto a point particle. So that's the first theory. So we'll imagine that we have an isolated black hole, some object of that form, placed in some sort of long wavelength external gravitational field. So the external gravitational field is described by some metric that varies slowly relative to, so the scale over which it varies is large compared to the size of the objects that we're dealing with. So you have some black hole sitting in space, moving through space in some way, and here's the gravitational field is much bigger than it, or very slowly compared to it. And in that limit, of course, the intuition is that you can replace the black hole just by a point object moving through space-time, a world line, if you like. So this world line is characterized by some trajectory, depends on some parameter lambda. It has a tangent vector, the 4 velocity. And it's not the only degree of freedom associated with this object, because the original black hole could also, for example, spin around some axis, and that's a long wavelength fluctuation in this problem. That's a relevant mode. That's a massless mode, if you like. So the relevant degrees of freedom in this effective theory are, in addition to the space-time metric, which fluctuates, and in addition to the world line of the object and the 4 velocity x dot, we have also, in order to describe the spin of this black hole, we need to specify a frame that moves along the object. So it's some frame that's orthogonal to the 4 velocity, so it consists of 3 normalized vectors, 1, 2, 3. And that also plays a role in describing what this object is. So this frame field, it lives on the world line. It's localized on the object. Just tells you how this thing rotates relative to other frames at infinity. And then the idea, as usual, is you just write down, so these are the things that show up in the theory, and then as in any other effective theory, you write down the most general action consistent with the symmetries. The symmetries of this problem are first of all, you have diffeomorphisms. In other words, coordinate transformations, because this is general relativity, so you're allowed to change your coordinates from x to x prime, which is a function of x, in an arbitrary way. And every term in the action better respect that symmetry. The other thing you have is reparameterization invariance. The parameter along the world line is totally up to you, totally arbitrary, so you can modify it any way you like, and the action should respect that symmetry. So lambda could go to some other lambda bar or lambda tilde. And then you just start writing down terms. The action that describes at least a single point particle coupled to gravity is a gravitational term for G, and another term for the point particle. So the gravitational term, we'll just take it to be the usual Einstein gravity, so the Einstein-Hilbert action. That is just equal to, up to some constant, the integral of the scalar curvature. The constant in my conventions is called m Planck squared. It has units of mass squared. And then the action is just this, and this is two leading order derivatives. Well, that's what it is. That defines general relativity. My choice of units, even though this is a classical problem, is to set h bar equal to c equal to 1. The reason why we do that is because, well, it's easier to write down Feynman rules when there's no h bars and c's around. Of course, they drop out of any observable that you compute. When you take h bar to 0, is what you get. So there's no harm in keeping h bar equal to 1. And so, in terms of perhaps more familiar quantities, this m Planck is just it's related to Newton's constant of gravity by that formula, it turns out. So that's the Einstein term, and then there's the terms that describe the point particle. Again, the idea is to just write down everything consistent with the symmetries of the problem. So the simplest thing you could write down involves looks just like that. It's m d tau, where d tau is just the proper time. It's given by that, and it's evaluated on the world line. That's that. And then after that, there's terms that describe, for instance, how the spin couples to gravity, and also how the spin precesses, so the kinetic term for the spin. It involves something called the spin connection, which is a spin connection that you derive from the frame for this frame. Let me not give you the details, because in this introduction I don't want to talk about spin, but I'm writing it down now, and I won't write it again. So there's that term. This is the actual spin of the black hole. Details on how to work out this is the right term for spin are in a paper by Orto from 2005. I'll put all the relevant references on the webpage associated with the course. Then you keep going to whatever order you need, and then the next terms that you can write down involve couplings of the particle to the curvature of space-time. So these are terms that you can write like this. Where this E and B are components of the curvature tensor projected onto the particle. So E and B refer to the parity transformation properties of these objects. E is called the electric type parity component of the Riemann tensor. It is explicitly given by an expression that looks like this: R mu alpha mu beta V mu V nu E alpha A E beta B. So it has parity even, and then there's the magnetic one. It's parity odd, but all that matters is they're just components of the curvature tensor. And by diffeomorphism invariance, everything has to be contracted together. So it's E squared plus B squared. Those are the only two terms that are possible beyond the minimal point particle. So VAB is some other expression.
Can you explain a little bit physically what the E's and B's are? I mean, they're projected.
Yeah, I will in a second. You know, the whole idea is you don't have to. They're just there. They're the terms that are allowed by the symmetries. Of course, they give rise to specific physical effects, which I'll discuss in a minute. Mm-hmm. But the idea is, look, you are completely agnostic about the physics, right? You just write down everything that's consistent with the symmetries. And what's going to happen is that these coefficients will scale like more and more powers of the size of the object, so there'll be smaller and smaller contributions at a given order. But yeah, I will say exactly what they correspond to in a second. So B, just to be complete, involves the epsilon tensor. So anyway, and of course this goes on forever, and what allows you to stop is that you're only interested in calculations up to some fixed order, determined by the actual experiment that you're trying to describe. So the question is, what do these things mean? Well, to understand what they mean, let's just ignore them first, and let's just look at this term, right? This term predicts that, so if you just vary this and set the variation to 0, then m d tau gives you the geodesic equation. So it tells you, so if you ignore all this other stuff, it tells you that the thing moves in a geodesic. That's exactly what a point object is supposed to do in a gravitational field by the equivalence principle. But if the object is not a point object, but it actually has a finite size, then it's not going to fall in a geodesic, because there's tidal forces tugging at it from different directions in this external gravitational field. So it is precisely these terms that give you that. So in other words, if you add these terms to the action, then it's no longer a geodesic motion. Now it's non-geodesic motion because it's not free-falling, really. I mean, different parts of it are free-falling, but they're accelerated relative to each other. And that's what they are. So these coefficients C and E, in particular, measure the tidal response. They tell you what the object is doing when you place it in a gravitational field. So that's what you're supposed to think about. If you actually were to work out the dimensional analysis, you would learn that these coefficients E and B just generically should scale like the size of the object to the 4. In our units, you have to put an n blank. Let me not explain that. I will explain the power counting for the theory in more detail later. So let me not explain this now. But it just, in a sense, follows from dimensional analysis. It turns out that For a black hole, it was found recently in a paper by Steinhoff and collaborators from, I think, 2013, that these coefficients are actually 0, which is quite puzzling to me because it seems to indicate that a black hole has no tidal response, at least to static electric fields. What they found, though, is that even though these coefficients are 0, the leading non-zero coefficients for a black hole involve derivatives acting on this EMP. So it means that if you place a black hole in a static field, somehow it doesn't distort. But if the field is wiggling, then it distorts. So it's a very puzzling result that I don't think is fully understood yet, but it is, I believe, mathematically correct. And you can go read the paper if you're more interested. Anyway, this gives you hopefully an idea of how you write down these point particle actions. You just use the symmetries as a guide, and the interpretation of the terms is that they code tidal response. And I am, in what follows, because I'm just going to present the basic story, that I ignore spin. Again, you can look up this paper by Porto from 2005 to see how spin comes in. I'm also going to ignore things like dissipation, which for a black hole, it's something that you really shouldn't ignore because black holes absorb particles, right? I mean, that's, they have an event horizon. Dissipation can also be included into the formalism, and that was in a paper by Ira and myself from 2005 or 6. So this is black hole absorption. So certainly one can include it, but I don't have time to talk